Fermat's sum of two squares theorem, which states that every prime of modularity 4n plus 1 can be written as the sum of two integers squared, and the Sieve of Eratosthenes. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. The simpleton's mathematical coat of arms. In Euclid we trust, and not the mathematicians. We know that the totality of the integers is a complete number field, so that there cannot be a missing one even though they become infinitely large and beyond our ability to write them down, because common sense and reasoning tells us so. So to demonstrate that there is not one prime in the infinity of primes of modularity 4n plus 1 that is not a sum of two squares, we only need to show that the reduced number field they produce is total, so that no exclusions can occur, and consequently no change in their behaviour. So contrary to what we are told, the fact that all known primes of modularity 4n plus 1 are the sum of two squares is in fact proved to infinity, and what we have is a speculative conjecture based on stupidity. We take 1.25 and add 1 to it repeatedly ad infinitum, and then multiply all by 4, so that we have the totality of all integers of modularity for n plus 1, with not one exception. That not one for n plus 3 prime is present is self-evident. However, we notice that 1, 3 squared equals 9, and 7 squared equals 49 are present. Also, we see that 3 times 7 equals 21 is present, but 2, 7 times 9 and 3 times 49 are not, as are 3 times 5, or 5 times 7, or 3 times 13, or 7 times 13, or 3 times 17, or 7 times 17. That is because in 1, the product of 4n plus 3 times 4n plus 3 has modularity 4n plus 1, whether mixed or a square, and must therefore be in the list. In fact, every even power of 4n plus 3 will be in the list, as will the composite of every even group of 4n plus 3 terms. 2. The examples given are all 4n plus 1 times 4n plus 3 combinations, which retain modularity 4n plus 3, so are not in the list. This applies to all odd groups of 4n plus 3 terms, which will never be in the list. So now we apply the sieve of Eratosthenes, but in a slightly modified way, as we only want to remove 4n plus 1 composites resulting from 4n plus 3 primes. So we remove 3 times 7, 11, 19, 23, 31, 43, 47, 51, and so on. The surprising but not totally unexpected thing is that multiples of 3 are spaced every third position, so it is almost a perfect sieve for all 4n plus 3 primes. We do have all even powers of 3 present, i.e. 9, 18, 1, 729, etc. Also, these even powers, all being squares, multiply through all sums of two squares to give another sum of two squares. Hence, 45 equals 9 times 5 equals 3 squared times 5 equals 3 squared times 2 squared plus 1 squared equals 6 squared plus 3 squared equals 36 plus 9 equals 45. Euler considered all 4n plus 3 squares to be the sum of two squares, of the form 4n plus 3 squared plus 0 squared, and I'm inclined to agree with him. I have graded them out, and they will stay in the list. We now repeat the same for 7, where again every seventh number after 21 is a multiple of 7. Apart from 1 times 7 squared equals 49 equals 7 squared plus 0 squared, then 5 times 7 squared equals 245 equals 7 squared plus 14 squared, and 13 times 7 squared equals 637 equals 21 squared plus 14 squared, and 17 times 7 squared equals 833 equals 28 squared plus 7 squared. Note that 7 is a factor of the roots. We now repeat the same for 11, where again every 11th number after 33 is a multiple of 11. We now repeat the same for 19, where again every 19th number after 57 is a multiple of 19. We now repeat the same for 23, where again the 23rd number after 69 is a multiple of 23, and we can repeat the process ad infinitum for all other 4n plus 3 primes. Condensing what we have done so far, we end up with the following table, where the rows have been eliminated and the resulting number field are all of modularity 4n plus 1, and all are the sum of two squares. Since we are only dealing with odd integers, the sum of two squares must contain one even and one odd square, since odd plus odd and even plus even always produce an even output. The 4n plus 1 primes are in red and the composites are in black. Note that the binary composites have two sums of two squares, and we find that the number of sums of two squares increase rapidly the greater the number of primes or factors that they contain, i.e. 5 times 13 times 17 equals 1105 has 6 sum of two squares solutions. So how on earth can a 4n plus 1 prime not be a sum of two squares, which are a bigger infinity than the primes, so that there are plenty to go round? And how would the composites it makes with other 4n plus 1 primes behave with regard to the formation of sums of two squares? Also, the results we get from sieving and direct computation via the sums of two squares are identical, and therefore the conclusion that every 4n plus 1 prime must be the sum of two squares is irrefutable. QED. So I will finish with the small but completed table, which can be extended indefinitely by the same means already carried out. Just one final comment, which is that the table should really have started with 0 plus a quarter equals 1 equals 1 squared plus 0 squared, but its omission is not of importance on this occasion.